What if I told you that the future of space could hold the key to traveling through time, or even building entire civilizations among the stars? We've long pondered the infinite possibilities of space, and with each discovery, our curiosity only grows. The endless expanse above us teases countless outcomes, each more fascinating than the last. In this video, we're going to explore two of the most captivating concepts for the future of space: time travel and space habitats. Time travel, a concept often relegated to the realms of science fiction, might not be as far-fetched as it seems. We'll dig deep into how theories from some of our greatest minds, like Einstein, could one day allow us to manipulate time, use black holes to our advantage, and perhaps even crack the code of temporal travel. On the other hand, space habitats offer a glimpse into how humanity might one day expand beyond Earth. Imagine O'Neill cylinders, massive, rotating colonies in space where entire civilizations could thrive. We'll explore what it would take to build these ambitious structures, the challenges involved, and the potential timeline for making them a reality. Before we embark on this journey, all we ask is that you approach these ideas with an open mind. Are we close to achieving time travel? The short answer is no. We're not sure if it's even possible. However, if it is, the theories we'll dive into could show us the way. And while we don't have space colonies orbiting Earth just yet, some of the world's most brilliant minds and wealthiest entrepreneurs are working tirelessly to make this a possibility. So, open your mind and imagine what it would be like if these theories came true, because you never know. We may be on the cusp of achieving the impossible. Now, without further ado, let's start with time travel concepts, particularly with wormholes and Einstein-Rosen bridges. Let us start our future of space journey by exploring a concept that stretches the boundaries of what we think is possible: the idea of wormholes and Einstein-Rosen bridges. These ideas come straight from Einstein's general theory of relativity, suggesting that space itself might have hidden tunnels, shortcuts that could allow us to travel across vast distances in the blink of an eye. Think of space-time as a gigantic flexible sheet, like a bed sheet stretched out tight. Normally, to get from one side of this sheet to the other, you would have to travel across its surface, which could take an incredibly long time. But what if you could fold the sheet, bringing two distant points close together? A wormhole would be like poking a hole through the folded sheet, creating a tunnel that lets you step from one side to the other in an instant. The tunnel could connect two places that might otherwise be light years apart, offering a much faster route. Wormholes are more than just simple tunnels. They are born from the intense warping of space-time caused by massive objects like black holes. When a star collapses under its own gravity, it can create a black hole, a region where the pull of gravity is so strong that nothing, not even light, can escape. This extreme bending of space-time is what could potentially create a wormhole, a bridge between two distant parts of the universe. But these wormholes are not stable. The Einstein-Rosen bridge, a specific type of wormhole predicted by Einstein's equations, would collapse almost as soon as it formed. It would snap shut before anything could pass through. To keep a wormhole open, you would need something extraordinary, something called exotic matter. Exotic matter is unlike anything we experience in our daily lives. It has negative energy, which is hard to picture because everything we know, from the food we eat to the sunlight we feel, carries positive energy. This exotic matter could, in theory, hold a wormhole open, But so far, we've only seen hints of such material in very specific, tiny quantum experiments. Traveling through a wormhole, if it were possible, would be like stepping through a door that not only takes you to another place, but could also take you to another time. These tunnels might not just link different parts of our universe, but they could also connect entirely different universes or even different points in time, offering a way to travel into the future or the past. However, these ideas remain purely theoretical. No one has ever found a wormhole, and our current technology is nowhere near advanced enough to create or even stabilize one. The concept is filled with challenges. For example, the intense gravity inside a wormhole could stretch and squeeze anything trying to pass through, and the requirement for exotic matter adds another layer of difficulty. Despite these obstacles, the idea of wormholes continues to capture our imagination. The thought that the universe might hide such extraordinary pathways pushes us to think beyond what we know and explore the unknown. As we continue our journey through the future of space, the concept of wormholes and Einstein-Rosen bridges encourages us to consider the incredible possibilities that could exist out there, far beyond our current reach. Let's journey further into the future of space exploration by diving into the fascinating concept of the Tipler cylinder. This theoretical structure opens a window into the possibility of time travel, a notion that stretches the imagination and challenges our understanding of physics. To fully appreciate the Tipler cylinder, we need to ground ourselves in the basics of how it works, and from there, let the story unfold. The idea of a Tipler cylinder begins with the understanding that space and time are not separate entities, but are woven together into a fabric known as space-time. This fabric is not rigid. It can be twisted, bent, and stretched by the presence of massive objects. The concept of the Tipler cylinder takes this one step further. Picture a cylinder of immense size, not just a few meters or even kilometers long, but extending potentially to infinity. This cylinder, under the right conditions, could twist space-time so dramatically that it creates a path not just through space, but through time as well. The Tipler cylinder was first theorized as a solution within the framework of general relativity, a theory that already gave us the understanding that massive objects like planets and stars curve space-time around them. But what if, instead of a planet or star, we had a massive, incredibly dense cylinder spinning at an unimaginable speed? According to the theory, the rotation of such a cylinder would drag space-time along with it, creating a unique effect. This dragging of space-time is what could potentially allow for time travel. To visualize this, imagine a straight road that represents time. Under normal circumstances, you can only travel forward on this road. But the Tipler cylinder, by twisting space-time, could bend this road into a loop, allowing you to move forward, backward, or even return to your starting point at a different time. In other words, if you were to travel close to this spinning cylinder in a precise, carefully plotted path, you could find yourself on a journey through time, returning to a point in the past, or leaping forward into the future. The key to this time travel lies in something called a closed time-like curve, or CTC. A CTC is essentially a path in space-time that loops back on itself. In simpler terms, it's a route that, under the right conditions, allows you to end up where you started, not just in space, but in time as well. The Tipler cylinder, with its immense mass and rapid rotation, theoretically creates these CTCs, offering a route through time. However, the concept of the Tipler cylinder is not without its challenges. For one, the cylinder would need to be infinitely long for the equations to work out perfectly, a requirement that presents obvious practical issues. Infinite structures are not something we encounter in our daily experience, and building anything of infinite length is, of course, beyond our capabilities. But even if we imagine a cylinder of finite length, the mathematics suggests that under certain conditions, a finite tipless cylinder might still create closed time like curves if it spins fast enough. The idea of a spinning cylinder warping space-time is fascinating, but it also comes with significant dangers. The immense gravitational forces at play would likely cause extreme tidal effects, potentially tearing apart anything that ventured too close. Moreover, the ends of the cylinder, where the effects of the rotation are less stable, could be regions of intense instability. These areas might produce unpredictable results, making any journey near a tipless cylinder a perilous adventure. Another challenge comes from the requirement for exotic matter. For a finite tipless cylinder to function as a time machine, it might need a type of matter that possesses negative energy. Exotic matter is a concept that exists in the realm of theoretical physics, and while it's been discussed in relation to other concepts like wormholes, it remains purely hypothetical. The existence of such matter is not proven, and without it, the stability of a tipless cylinder's closed time-like curves would be questionable at best. Let's now visualize what it might be like to embark on a journey using a tipless cylinder. Imagine a spacecraft carefully approaching this enormous rotating structure. The ship would need to navigate with precision, following a spiral path around the cylinder. As it does so, the fabric of space-time around the ship begins to twist. The ship's onboard clocks, which have always ticked forward in time, might start behaving strangely, slowing down, stopping, or even running backward as the ship follows the curve of the cylinder. The ship's crew would be in uncharted territory. Outside the windows, the stars might seem to shift in strange ways, moving in patterns that defy normal experience. The very concept of before and after could blur, with the crew experiencing events in a non-linear sequence. A trip around the cylinder could bring them back to a point in time before they left, allowing them to witness events that had already occurred or even interact with their past selves. But this is where the paradoxes of time travel enter the picture. What if they changed something in the past? The idea of going back and altering history is fraught with complications, leading to the classic time travel paradoxes that have long been a staple of science fiction. The tipless cylinder, while a captivating idea, also raises profound questions about causality and the nature of time itself. If it were possible to travel back in time, would it be possible to change the past? Or would some principle prevent such changes? One proposed solution to these paradoxes is the Novikov self-consistency principle, which suggests that any actions taken by a time traveler were always part of history and therefore cannot change it. In other words, if you traveled back in time and attempted to change something, the very attempt would be part of the timeline you left and would not alter the course of events. Despite the theoretical challenges, the tipless cylinder continues to captivate the imagination of physicists and science enthusiasts alike. It represents a bridge between the known and the unknown, a tantalizing possibility that stretches our understanding of the universe. While it may never be built, the idea of the tipless cylinder pushes the boundaries of what we consider possible, challenging us to think in new ways about time, space, and the nature of reality. The concept of a tipless cylinder is a powerful example of how the laws of physics can lead to extraordinary conclusions, even if those conclusions seem out of reach with our current technology. The idea that time travel could be possible, that we could move backward or forward in time by following the right path through space-time, is both thrilling and daunting. It invites us to ponder not just the technical challenges of such an endeavor, but the philosophical implications as well. In the context of the future of space exploration, the Tipler cylinder is more than just a theoretical construct. It's a symbol of humanity's unending curiosity and our drive to explore the unknown. Even if we never build a time machine, the very act of considering such possibilities expands our horizons, pushing us to think more deeply about the universe and our place within it. As we look to the future, the Tipler cylinder reminds us that space is not just a vast, empty void. It's a canvas on which the laws of physics paint some of the most incredible, mind-bending possibilities. The future of space, with all its potential for exploration and discovery, holds more than just new planets and stars to visit. It holds the potential to unlock the very secrets of time itself, to find ways to move through the fourth dimension as easily as we move through the first three. In conclusion, the Tipler cylinder is a testament to the power of theoretical physics to stretch the imagination. It's a concept that, while grounded in the equations of general relativity, opens up possibilities that are almost too incredible to comprehend. It challenges us to think beyond the limits of what we know, to explore the edges of our understanding, and to dream of a future where the impossible might just become possible. Whether or not we ever build a Tipler cylinder, the journey it represents, the journey of discovery, of pushing boundaries, and of exploring the deepest mysteries of the universe, is one that will continue to inspire generations to come. As we stand on the cusp of a new era of space exploration, concepts like the Tipler cylinder remind us that the future of space is not just about new technologies or new destinations. It's about new ways of thinking, new ways of understanding the universe, and new possibilities that we have yet to even fully grasp. The Tipler cylinder, with its promise of time travel and its challenges to our understanding of physics, is just one of the many incredible ideas that await us as we venture further into the cosmos. As we continue our exploration into the future of space and time travel, we now arrive at the mind-bending concept of quantum tunneling. This phenomenon, rooted deeply in the principles of quantum mechanics, challenges our everyday understanding of how the universe works and offers tantalizing possibilities for time travel. Unlike other theoretical methods of time manipulation, quantum tunneling doesn't rely on massive rotating structures or infinite cylinders, but instead on the mysterious behavior of particles at the smallest scales of the universe. Quantum tunneling occurs when a particle manages to pass through a barrier that, according to classical physics, it shouldn't be able to penetrate. To visualize this, think of a ball rolling up a hill. If the ball doesn't have enough energy, it will roll back down, unable to reach the top. However, in the quantum world, particles don't behave like solid objects bound by classical rules. Instead, they exhibit wave-like properties, spreading out over space. Because of this wave-like nature, even if a particle doesn't have enough energy to go over the barrier, there's a small but real chance that it will simply appear on the other side, as if it had tunneled through the obstacle. This phenomenon is a direct result of the strange rules that govern quantum mechanics. Particles, whether they are electrons, protons, or any other fundamental building blocks of matter, are described not just by their position and momentum, but by a wave function that represents all the possible places where the particle could be. When this wave encounters a barrier, most of it reflects back, but a portion of it can leak through, allowing the particle to emerge on the other side. To better understand this, let's take a closer look at what happens when quantum tunneling occurs. Imagine a particle approaching a barrier. In classical physics, the particle would either have enough energy to overcome the barrier, or it wouldn't. But in quantum mechanics, the particle's wave function begins to interact with the barrier in a unique way. As the wave function spreads out and encounters the obstacle, part of it decays within the barrier itself, and this decayed portion can still carry the particle to the other side. One of the most fascinating aspects of quantum tunneling is how it appears to violate our intuitive sense of time and space. In some scenarios, the particle that has tunneled through the barrier seems to arrive on the other side faster than light could travel that distance. This doesn't mean that the particle actually travels faster than light. Such a thing would violate the known laws of physics. Instead, it's a quirk of how the wave function behaves. The particle doesn't actually speed through the barrier. Rather, the barrier itself alters the spread of the wave function in such a way that the particle appears on the other side almost instantly. The implications of quantum tunneling for time travel are intriguing. If a particle can tunnel through a barrier that it seemingly shouldn't be able to penetrate, could this be harnessed to allow particles or even larger objects to traverse not just space but time as well? While this remains purely theoretical, the notion that particles can bypass the conventional flow of time and space offers a glimpse into a future where the boundaries of these dimensions might be more flexible than we currently understand. Quantum tunneling isn't just a theoretical curiosity. It's a well-documented phenomenon with practical applications. For instance, it's the principle behind technologies like scanning tunneling microscopes, which allows scientists to see structures at the atomic level by detecting the tunneling of electrons. It also plays a role in the workings of some modern electronics, where tiny currents pass through barriers within semiconductor devices due to tunneling effects. In the context of time travel, quantum tunneling introduces the idea that under the right conditions, particles could potentially move backward in time. This isn't time travel in the way we often think about it, no DeLorean speeding back to 1955, but rather a subtle bending of the rules of cause and effect on a quantum level. If particles can borrow energy to tunnel through barriers, could they also borrow time? Could quantum tunneling be the key to accessing different points in time, allowing information and perhaps one day matter to slip through the cracks of our chronological understanding? The theory behind quantum tunneling suggests that the particle, when it interacts with the barrier, briefly enters a different state, a kind of liminal space where the usual rules don't apply. It's as if the particle is momentarily freed from the constraints of its surroundings, able to take a shortcut through time and space. In this state, the particle's interaction with time becomes more fluid, more flexible. It's a tantalizing thought, one that raises more questions than it answers. Imagine a scenario where, instead of a small particle, we could scale up the quantum tunneling process. Could this allow larger objects or even humans to take similar shortcuts through space-time? Theoretically, if quantum tunneling could be controlled and harnessed, it might one day be possible to move not just through space, but through time itself. The challenge, of course, is that quantum effects like tunneling are incredibly delicate. They occur on scales much smaller than what we're used to, and scaling them up to the macroscopic world presents significant challenges. But the idea isn't as far-fetched as it might seem. Scientists have already demonstrated that quantum tunneling is not instantaneous, as once thought, but takes a finite amount of time, albeit incredibly short. This means that during the tunneling process, the particle is in a state that's neither here nor there, neither in the past nor in the future. It exists in a kind of quantum limbo, where the normal rules of time don't necessarily apply. If we could understand and manipulate this state, we might be able to influence how particles and potentially larger objects interact with time itself. One of the more fascinating aspects of quantum tunneling is how it aligns with the concept of wave-particle duality, where particles like electrons exhibit both wave-like and particle-like properties. When a particle tunnels through a barrier, it's not doing so in the way a classical object would push through an obstacle. Instead, it's as if the particle's wave function allows it to bypass the barrier entirely, finding a path where none should exist. This bending of the rules is what makes quantum tunneling so captivating as a potential method of time travel. If we consider time as another dimension similar to space, quantum tunneling might be the key to moving through this dimension in ways that aren't normally possible. Just as the particle's wave function allows it to bypass spatial barriers, could it also allow the particle to bypass temporal barriers, slipping through time to emerge at a different point? The answer remains elusive, but the possibilities are staggering. In this vision of the future, time travel wouldn't involve speeding up or slowing down, as in traditional science fiction. Instead, it would be about finding and exploiting the loopholes in the fabric of reality itself. Quantum tunneling suggests that these loopholes exist, at least on a microscopic scale. The challenge for future scientists and engineers will be to understand these processes well enough to scale them up, to turn the quantum trick of tunneling into a tool for time travel. Quantum tunneling, then, offers a glimpse into a future where time travel might be more about subtle shifts and nudges than grand, sweeping movements through the ages. It's a vision of time travel that's quiet, almost hidden, working within the fabric of the universe's deepest laws. It challenges us to rethink what we know about time and space, to see them not as rigid constructs, but as flexible, malleable dimensions that can be bent and shaped under the right conditions. As we stand at the threshold of this new understanding, quantum tunneling reminds us that the universe is full of surprises. It's a place where the impossible might just be possible, where particles can pass through barriers, and perhaps one day, where time itself can be navigated in ways we have only begun to imagine. The future of space and time travel is not just about reaching distant stars, but about discovering the hidden pathways that connect every point in space and time, pathways that quantum tunneling hints at just beyond our current reach. The chronology protection conjecture is a fascinating idea that suggests the laws of physics might have built-in safeguards to stop time travel before it begins. This concept, rooted in the complex relationship between general relativity and quantum mechanics, introduces the possibility that even if we find a way to navigate through time, the universe won't let us change the past. The idea starts with closed time-like curves, theoretical paths through space-time that could, in principle, allows someone to loop back to an earlier point in time. These curves are not just the stuff of science fiction. They emerge naturally from Einstein's equations of general relativity under certain extreme conditions. However, they also present a serious challenge. They could create paradoxes, like the classic scenario where someone travels back in time and prevents their own existence. The chronology protection conjecture proposes that something in the laws of physics steps in to prevent these paradoxes from happening on a large scale, keeping the timeline intact. One way this protection might occur is through the buildup of quantum effects in and around the conditions that would allow time travel. When these effects interact with intense gravitational fields, like those near a potential time travel device, such as a wormhole, they might grow so large that they disrupt the device itself. This could prevent the formation of a stable pathway through time, effectively shutting down the possibility of time travel before it can occur. Imagine standing on the edge of a wormhole, ready to step through and journey to the past. According to this conjecture, just as you're about to take that step, the universe itself might intervene. The very laws of quantum mechanics could cause the wormhole to collapse, closing the door to the past and keeping the timeline secure. This isn't just a hypothetical scenario. It's a natural consequence of the interaction between gravity and quantum mechanics, suggesting that the universe might have a built-in mechanism to protect itself from the potential chaos of time travel. While this might sound like a cosmic safeguard, it also raises questions about the true nature of time. If time travel is theoretically possible, but practically prevented by these quantum effects, what does that say about time itself? Is time something that can be bent and twisted at will, or is it more rigid, with hidden rules that keep it flowing in one direction? The chronology protection conjecture doesn't just stop us from time traveling, it forces us to rethink what time really is. Could it be that time is a more complex and intricate part of the universe than we've ever imagined? Perhaps it's not just a straight line stretching from the past to the future, but a delicate web that the universe works tirelessly to keep intact. Even as we explore the possibilities of time travel through theoretical constructs like wormholes and rotating cylinders, this conjecture stands as a reminder that the universe might have its own plans. It suggests that there could be fundamental limits to what we can achieve with time travel, limits that are as much a part of the universe as the speed of light or the force of gravity. In the end, the chronology protection conjecture challenges us to think about time not just as a backdrop for our actions, but as an active player in the cosmic drama. It's a concept that keeps time travel in the realm of possibility, while simultaneously reminding us that some doors might remain closed, no matter how much we learn about the universe. We've pushed the boundaries of time travel theories, exploring the edges of what could be possible in bending time itself. Now, it's time to turn our attention to a different, yet equally thrilling frontier: space colonies. Moving from the abstract concepts of time travel to the more tangible possibilities of living beyond Earth, we enter a realm where humanity's future might very well lie. This isn't just about visiting other worlds, it's about the incredible challenge of creating sustainable environments where we can thrive far from our home planet. Let's shift our focus now to what it takes to build these new worlds among the stars. As we transition into exploring the future of space habitats, one concept that captures the imagination and scientific curiosity alike is the O'Neill cylinder. These colossal, rotating space habitats first envisioned by physicist Gerard K. O'Neill in the 1970s, offer a glimpse into what could be a reality for humanity, a home among the stars. An O'Neill cylinder isn't just a theoretical structure. It's a vision of what life could be like beyond Earth, in a self-sustaining environment that provides everything we need to thrive. Imagine a massive cylindrical structure floating in space, each end of the cylinder stretching miles into the distance. This isn't just a spaceship or a temporary station, but a fully fledged colony capable of housing thousands, if not millions, of people. The design of the O'Neill cylinder is both elegant and functional. Picture two cylinders, each about 20 miles long and 5 miles in diameter, rotating in opposite directions. This counter-rotation is crucial because it cancels out any gyroscopic effects, ensuring that the cylinders remain stable and properly oriented toward the sun. Inside these cylinders, the rotation provides artificial gravity, simulating the conditions of Earth so that inhabitants can live and move just as they would back home. But what makes the O'Neill cylinder truly fascinating is not just its size or rotation, it's the idea that it could be a complete ecosystem capable of supporting human life indefinitely. Imagine stepping inside one of these cylinders. The first thing you might notice is the vastness of the interior. The entire island of Manhattan could fit comfortably within one of these cylinders, with room to spare. The cylinder's interior surface is lined with strips of habitable land, with alternating sections of transparent windows that allow sunlight to flood the environment. These windows are not just ordinary panes of glass, but complex systems designed to control the light and atmosphere inside the cylinder. Mirrors positioned outside the windows reflect sunlight into the habitat, creating a day-night cycle that mirrors Earth's. When it's time for night, the mirrors can be adjusted to reveal the dark expanse of space, allowing heat to escape and giving the residents a glimpse of the stars beyond. The air inside the cylinder would be carefully managed to ensure a breathable atmosphere similar to Earth's. By maintaining oxygen and nitrogen at partial pressures close to what we experience at sea level, the habitat can provide a comfortable environment for its inhabitants. The size of the cylinder also allows for something quite extraordinary: a small, self-contained weather system. This means that rain, clouds, and even small storms could occur naturally, just as they do on Earth. The artificial gravity created by the rotation of the cylinder ensures that residents can walk, run, and live their daily lives without feeling the disorienting effects of weightlessness. Sports like soccer, tennis, and even skiing could be enjoyed inside the cylinder. The rotation creates a gravitational pull that would allow for mountain climbing and sailing on artificial lakes, with the added excitement of knowing that one wrong step could send you tumbling in a direction that doesn't quite align with Earth's gravity. The design also incorporates areas specifically for agriculture. These agricultural rings, rotating at different speeds than the main habitat, provide space for growing food, ensuring that the colony can be self-sufficient. These rings are designed to harness the energy from the sun, using advanced techniques to grow crops more efficiently than we can on Earth. Imagine fields of wheat, orchards of fruit trees, and greenhouses full of vegetables, all thriving in the controlled environment of the cylinder. One of the most impressive aspects of the O'Neill cylinder is its potential for sustainability. By using materials sourced from the moon and asteroids, the colony can be built without the immense cost and energy required to launch these materials from Earth. Mass drivers, or electromagnetic catapults, could be used to launch raw materials from the moon's surface, where they would be collected, and used to construct and maintain the cylinder. As you wander through the cylinder, you might notice how the environment can be manipulated to suit the needs of the inhabitants. The amount of sunlight can be controlled by adjusting the mirrors, which could also be used to create different climates within different sections of the cylinder. Want to live in a tropical paradise? There's a section for that. Prefer the cool, crisp air of a temperate forest? Just head to another part of the cylinder. Living in an O'Neill cylinder could offer a lifestyle that's not only sustainable, but also superior to life on Earth in many ways. With controlled weather, abundant food, and no pollution from combustion engines, these space habitats could represent an ideal living environment. The freedom from Earth's environmental issues could lead to a higher quality of life, with residents enjoying clean air, fresh water, and a stable climate year-round. But how would these cylinders stay oriented toward the sun? The design cleverly uses the principles of gyroscopic motion. By carefully managing the rotation of the two counter-rotating cylinders, the entire habitat can be kept perfectly aligned with the sun, ensuring that it receives a constant supply of solar energy. This energy is crucial not just for providing light, but also for powering the entire colony. As you move closer to the center of the cylinder, gravity starts to lessen. At the very center, there's a region of zero gravity where the effects of the rotation cancel out. This area could be used for recreation, allowing inhabitants to experience weightlessness without leaving the habitat. It could also serve as a hub for scientific research, where experiments that require microgravity can be conducted. One of the key challenges in building an O'Neill cylinder is the need for radiation shielding. Space is filled with cosmic rays and other forms of radiation that could be harmful to human health. The cylinder's design addresses this by using the structure itself, as well as the air inside, to provide sufficient protection. Additionally, the sheer size of the habitat means that any radiation that does penetrate the outer shell is likely to be absorbed before it reaches the inhabitants. But perhaps the most exciting aspect of the O'Neill cylinder is its potential for expansion. These habitats could be the first step in a larger effort to colonize space. As technology advances and we learn more about living in space, these cylinders could be scaled up, creating entire networks of colonies throughout the solar system. Each cylinder could be connected to others, forming a web of human settlements that stretch across the stars. In conclusion, the O'Neill cylinder represents a bold vision for the future of space colonization. It's a concept that combines the best of human ingenuity with the limitless potential of space. As we continue to explore the possibilities of living beyond Earth, the O'Neill cylinder stands as a testament to what we can achieve when we dream big and think beyond the boundaries of our home planet. The future of space colonization might very well start with these rotating behemoths, spinning in the void, offering a new home for humanity among the stars. As we move deeper into the future of space colonization, we turn our attention to another fascinating concept, the Bernal Sphere. This spherical space habitat, first proposed by John Desmond Bernal in 1929, offers a unique vision of how humanity might one day live beyond Earth. Unlike the cylindrical design of the O'Neill cylinder, the Bernal Sphere imagines a self-sustaining, rotating sphere that could serve as a permanent home for thousands of people in space. The Bernal Sphere concept is intriguing not just for its shape, but for the lifestyle it proposes for its inhabitants. Picture a vast hollow sphere rotating slowly in the darkness of space. This rotation is key because it creates artificial gravity through centrifugal force, allowing those inside to experience the familiar pull of gravity, just as they would on Earth. The sphere itself would be large enough to house entire communities, complete with living spaces, work areas, and recreational facilities. One of the most compelling features of the Bernal Sphere is its self-sufficiency. Unlike the International Space Station or proposed lunar bases, the Bernal Sphere is designed to be entirely self-sustaining. The habitat would generate its own food, water, and oxygen through advanced agricultural techniques and recycling systems. Imagine fields of crops growing under the artificial sunlight, providing fresh produce for the inhabitants, while water is continuously recycled and purified, ensuring a constant supply for all. The sphere's rotation, besides creating gravity, also helps in maintaining a stable environment. The outer shell of the Bernal Sphere would be constructed from lightweight but durable materials, such as aluminum or steel, and lined with layers of insulation and radiation shielding. This would protect the inhabitants from the harsh conditions of space, including cosmic rays and extreme temperatures. Inside, the air would be kept at Earth-like pressures, with a carefully controlled atmosphere to ensure a safe and comfortable living environment. As you envision stepping inside the Bernal Sphere, the first thing that might strike you is the vastness of the interior. The sphere would be divided into different sections, each serving a specific purpose. Living quarters might resemble those found in a small town on Earth, complete with homes, schools, and shops. Recreational areas would offer parks, sports facilities, and even artificial lakes, allowing residents to enjoy a variety of activities in their free time. One of the unique aspects of the Bernal Sphere's design is its central corridor, which runs through the heart of the sphere. This corridor would connect all the different sections, making it easy for inhabitants to move from one area to another. Picture a bustling community where people live, work, and play, all within the safety of the sphere's protective walls. The artificial gravity generated by the sphere's rotation is crucial for the health and well-being of its inhabitants. In the microgravity environment of space, prolonged exposure can lead to a range of health issues, including muscle atrophy, bone density loss, and vision problems. By simulating gravity, the Bernal Sphere would help prevent these problems, allowing people to live and work in space for extended periods without suffering the adverse effects associated with weightlessness. The Bernal Sphere isn't just about providing a home, it's about creating a thriving ecosystem in space. The sphere would be designed to support its own biosphere, with plants, animals, and even small weather systems. The air would be kept fresh through the careful balance of oxygen and carbon dioxide, with plants playing a vital role in maintaining this balance. This self-contained ecosystem would allow the Bernal Sphere to function independently from Earth, making it a viable option for long-term space colonization. In terms of energy, the Bernal Sphere would be powered by solar panels or nuclear energy, providing a reliable and sustainable source of power. The solar panels would be strategically placed on the exterior of the sphere, capturing the sun's energy to power everything from lights to life support systems. This energy would be stored in batteries, ensuring that the habitat has a constant supply, even when it's not directly exposed to sunlight. The potential of the Bernal Sphere extends beyond just one habitat. Imagine a network of these spheres scattered throughout space, each one housing thousands of people and contributing to the expansion of human civilization beyond Earth. These spheres could be linked together, forming larger communities or even entire cities in space. They could serve as hubs for scientific research, manufacturing, or even tourism, offering a new frontier for human exploration and development. One of the advantages of the Bernal Sphere over other proposed space habitats is its scalability. The design can be adapted to different sizes depending on the needs of the community. Smaller spheres could serve as outposts or research stations, while larger ones could become bustling metropolises, each one a self-contained world in its own right. The vision of living in a Bernal Sphere challenges our current understanding of what life in space could be like. It offers a future where humans are not just visitors to space, but permanent residents, living in harmony with their environment. The design of the Bernal Sphere is not just about survival. It's about thriving in space, creating a society that is self-sufficient, sustainable, and capable of growing and evolving over time. The Stanford Torus represents one of the most iconic visions of space colonization, a concept born from the ingenuity and ambition of the 1975 NASA summer study. Imagine a massive, donut-shaped structure floating in the vastness of space, its circular form rotating gently to simulate the gravity we take for granted on Earth. This is no mere science fiction fantasy, but a detailed and thoroughly considered design capable of housing tens of thousands of people in a self-sustaining environment. At first glance, the Stanford Torus might resemble a giant ring spinning silently in the void. But this design is far more than a simple ring. It is a meticulously crafted habitat, engineered to provide not only the necessities of life, but also the comforts and beauty of a natural environment. The torus itself measures approximately 1.8 kilometers in diameter and rotates once per minute. This rotation creates a centrifugal force that simulates gravity on the inner surface of the ring, allowing inhabitants to walk, live, and work as they would on Earth. One of the most striking aspects of the Stanford Torus is its ability to simulate a natural environment within its curved walls. Picture a long, narrow valley that curves upward and eventually forms a complete circle overhead. This is what life inside the Stanford Torus would look like. The inner surface of the torus would be lined with homes, parks, and agricultural fields, creating a landscape that is both familiar and otherworldly. The population density inside the torus would be akin to that of a dense suburb, with areas dedicated to housing, agriculture, and communal spaces. The torus is connected to a central hub by a series of spokes. These spokes are not just structural supports, but vital conduits for people and materials moving between the hub and the living areas. The hub itself, located at the rotational axis of the station, experiences minimal artificial gravity, making it an ideal location for docking spacecraft and for industrial activities that benefit from low gravity. Imagine the ease with which residents and visitors could move from the gravity-rich environment of the torus to the near-weightless hub, a transition as simple as taking an elevator. Sunlight, essential for both human well-being and agriculture, is provided to the interior of the torus through a sophisticated system of mirrors. A large, non-rotating primary solar mirror captures sunlight and reflects it into the torus, creating a cycle of day and night that mimics the natural rhythm of Earth. As you walk through the lush green fields inside the torus, the sunlight streaming down would feel almost indistinguishable from that on Earth. Yet all of it is carefully managed and controlled from outside the station. Constructing such a colossal structure is no small feat. The Stanford Torus would require nearly 10 million tons of material, a challenge that would be met by mining resources from the moon, and possibly asteroids. These materials would be launched into space using mass accelerators, collected by a mass catcher stationed at a stable point in space, and then transported to the construction site. This process minimizes the need to transport materials from Earth, reducing costs and making the construction of the Taurus a more feasible endeavor. As you consider the design of the Stanford Taurus, it's clear that this habitat is more than just a place to live. It's a carefully engineered solution to the challenges of long-term space habitation. The rotating structure provides gravity, the mirror system ensures sunlight, and the spokes and hub facilitate movement and industry. Every aspect of the Taurus is designed with the well-being of its inhabitants in mind, offering a life that, while different from Earth, could be just as fulfilling and vibrant. The Stanford Taurus is not just a theoretical model, but a symbol of what human ingenuity can achieve. It represents a future where humans are not confined to Earth, but can thrive in self-sustaining habitats scattered across the solar system. As you visualize life inside the Stanford Taurus, it's easy to see how this design could one day become a reality, offering a new frontier for humanity to explore and inhabit. The concept of a Dyson sphere stands as one of the most ambitious and mind-bending ideas in the realm of space colonization and energy harnessing. It represents not just a megastructure, but a leap in our understanding of how an advanced civilization might manage its energy needs by fully utilizing the power of its star. Imagine a structure so vast that it completely surrounds a star, capturing nearly all of its energy output. This is the essence of a Dyson sphere. Unlike the traditional means of energy generation we use on Earth, which rely on limited resources, a Dyson sphere would allow a civilization to tap into the virtually limitless energy provided by its star, making it an ideal solution for the energy demands of a technologically advanced society. The Dyson sphere was first proposed by physicist Freeman Dyson in the 1960s, not as a literal blueprint, but as a theoretical concept to suggest how a civilization far more advanced than ours might solve its energy needs. The idea is that once a civilization reaches a point where the energy demands outstrip what can be provided by a planet, the next logical step would be to harvest energy directly from its star. This would involve constructing a massive structure or a network of structures around the star to collect and convert its radiant energy into usable power. A full Dyson sphere, as often depicted in science fiction, would be a solid shell completely encircling the star. However, such a structure presents numerous practical challenges, including immense material requirements, structural integrity issues, and thermal management problems. Instead, more feasible variations of the Dyson sphere concept have been proposed, such as a Dyson swarm, a collection of orbiting solar collectors or satellites that together capture a significant portion of the star's energy. These collectors would orbit the star in a carefully coordinated pattern, ensuring that they cover a large surface area without colliding with one another. Building a Dyson swarm would still be an extraordinary engineering challenge. The sheer scale of the project would require resources far beyond what we currently possess. It might involve the mining of entire planets or asteroids to gather the necessary materials. These materials would need to be light, yet strong enough to withstand the stresses of space and the intense radiation from the star. Advanced robotics and artificial intelligence would likely be essential for the construction and maintenance of such a vast array of satellites. One of the key advantages of a Dyson swarm over a solid Dyson sphere is its scalability. A swarm could be gradually expanded over time, as more satellites are built and launched, allowing a civilization to increase its energy capture incrementally. This modular approach makes the concept more feasible, though still far beyond our current technological capabilities. In addition to capturing solar energy, a Dyson sphere or swarm would also have significant implications for the civilization that constructs it. Such a structure could provide almost limitless energy, enabling technological advancements that are currently unimaginable. It could power vast computational networks, support massive populations, and even fuel interstellar travel. However, constructing a Dyson sphere would not be without its challenges. Managing the heat generated by such a structure is a significant concern. The energy collected would need to be dissipated or used in a way that prevents the structure from overheating. Advanced materials with high thermal conductivity and the ability to radiate excess heat into space would be essential. Additionally, the structure would need to be stable, with precise control mechanisms to ensure it remains in position around the star. The idea of Dyson spheres also raises intriguing questions in the search for extraterrestrial life. If advanced civilizations exist elsewhere in the universe, they might have constructed their own Dyson spheres. These megastructures would be detectable from Earth by their unique signatures, particularly the way they block and re-emit the star's light, which could create anomalies in the star's observed brightness or generate unusual infrared emissions. Despite the challenges, the Dyson sphere remains a powerful concept in the study of future technologies and the potential for advanced civilizations. It encapsulates the idea that as a society grows, so too does its need for energy, pushing the boundaries of what is possible in terms of engineering and resource management. While we are still far from being able to construct such a structure, the Dyson sphere remains a fascinating glimpse into the possible future of human civilization, or perhaps that of other civilizations that have already mastered the art of harnessing the power of their stars. As we draw to a close on this exploration of the future of space, it's clear that humanity's dreams extend far beyond the confines of our planet. We've dug deep into the mind-bending possibilities of time travel, from the potential shortcuts offered by wormholes to the dizzying complexities of Tipler cylinders. We've pondered the universe's own safeguards against the paradoxes of time travel through the chronology protection conjecture, and we've considered the quantum realm where particles might defy the very fabric of space and time. But our journey didn't stop at the edges of time. We've ventured into the realms of space colonization, where humanity might one day build new homes among the stars. The O'Neill cylinders offer a vision of vast, rotating habitats where entire communities could thrive, basking in the artificial sunlight and enjoying the comforts of Earth-like gravity. The Bernal spheres present a more intimate, self-sustaining environment, a spherical sanctuary floating in the void, designed to support life for generations to come. And the Stanford Torus, with its iconic ring shape, offers a blueprint for future space habitats that balance practicality with the potential for creating vibrant, natural environments. Finally, we explored the awe-inspiring concept of Dyson spheres, massive structures that could capture the energy of entire stars, whether through swarms of satellites or more ambitious designs. These megastructures represent the pinnacle of energy management, a step towards a future where humanity, or perhaps other advanced civilizations, harnesses the full power of the cosmos. These concepts, though theoretical, push the boundaries of what we consider possible. They challenge us to think beyond our current limitations and imagine a future where humanity isn't confined to one planet or one timeline. The future of space, as we've seen, is filled with potential. Potential that could one day transform our understanding of the universe and our place within it. As we look up at the stars, these ideas remind us that the future is not just something that happens to us. It's something we build, one idea, one discovery, one leap of imagination at a time. The journey into space is not just about exploring new worlds, but about expanding the limits of what humanity can achieve. And who knows, perhaps one day, the concepts we've discussed in this video will no longer be science fiction, but the reality of our existence in the vastness of space. Thank you for joining us on this journey through the future of space. As we continue to dream, explore, and innovate, the possibilities are as endless as the universe itself. Until next time, keep your eyes on the stars and your mind open to the infinite possibilities that lie ahead.